Welcome back, everyone. When scientists talk about life beyond Earth, they're not talking about spaceships flying to distant stars. Instead, they're talking about learning from light, because light is the only carrier of information that reaches us from other planetary systems. Every planet outside our solar system is extremely distant, so the only practical information we receive comes from photons that left that planet years or even centuries ago. Those photons interact with a planet's atmosphere or surface before traveling outward. By the time they arrive, they carry measurable changes that reflect those interactions. They also arrive weakened and delayed by distance. Physical travel is limited by propulsion energy and travel time, so for now and for many years into the future, observation defines the boundaries of what can be known. To help us answer the question of the possibility of life on other worlds, several tool systems work together to make this kind of observation possible. Telescopes are used to collect incoming light and concentrate it into a usable signal. Spectrometers are used to separate that light into different wavelengths, so chemical information can be extracted. Stabilization systems are used to keep measurements steady over long periods, so weak signals are not blurred or lost. Computers are used to organize and interpret the resulting data so physical descriptions can be constructed. Each system addresses a different requirement. None of them replaces the others. Over the next 10 years, progress will depend on how well these systems function together. Right now, observations describe planetary environments rather than living organisms themselves. Scientists measure how much starlight a planet blocks to estimate its size. They measure how often that blocking repeats to determine the planet's orbit, because orbital motion sets a regular timing pattern. When light passes through a planet's atmosphere, certain wavelengths are absorbed by specific gases. This reveals which gases are present. These measurements do not explain where those gases come from. A gas can appear through geology or chemistry as well as biology. In the search for possible life, the first requirement is persistence, meaning the same gases must appear repeatedly under similar conditions. Please subscribe. The first major limitation encountered after detection is photon collection. Distant planets reflect or emit only a tiny amount of light compared to their stars. Telescope mirror size controls how many photons can be gathered during an observation, because a larger surface intercepts more incoming light. Larger mirrors therefore improve measurement quality. However, larger mirrors must continue to remain precisely aligned to act as a single optical surface. A facility operated by the European Southern Observatory in Garching develops segmented mirrors that behave like one mirror when alignment is maintained. If the segments drift out of position, the collected light no longer focuses correctly. Signal quality then degrades immediately, and so mirror size helps only if alignment can be controlled. Even when enough photons are collected, the signal must remain stable during observation. Earth's atmosphere bends light unevenly as air density changes. Temperature changes cause telescope structures to expand or contract. These effects distort incoming wavefronts and smear planetary signals into background noise. Adaptive correction systems counter this distortion by adjusting mirror shapes in real time. These systems rely on fast sensing and precise movement to match changing conditions. If corrections fall behind distortion, clarity is lost. Once stability drops below a minimum threshold, longer observation just adds noise rather than information. Another limitation appears when collected light is split into wavelengths. Chemical fingerprints often lie close together in the spectrum. High resolution separates these features by dividing light into many narrow channels. However, this spreads photons across those channels and weakens the signal of each one. Low resolution concentrates photons into fewer channels, which preserves signal strength but blends chemical features together. A development program operated by the European Space Agency in Paris improves dispersive optics to increase separation efficiency. Engineers must balance chemical separation against photon scarcity for each planet they observe. When searching for evidence of possible life on other worlds, Atmospheric structure adds another constraint to interpretation. Pressure affects how wide absorption features appear, because higher pressure causes more molecular collisions. Temperature controls how strongly gases absorb or emit light by setting molecular energy states. Without pressure estimates, gas abundance can be badly misjudged. Temperature uncertainty changes which chemical reactions remain stable over time. A modeling group operated by the Italian Space Agency in Rome simulates layered atmospheres under different pressure and temperature conditions. These simulations define which atmospheric states can persist without continuous biologic replenishment. Repeated observation introduces scaling problems that tend to grow over time. To confirm stability, the same planet must be observed many times. Observations must span seasons and viewing angles to rule out temporary effects. Each observation adds data, and over years datasets become large and complex. Small calibration errors introduced early can distort trends later on. A data systems laboratory, operated by the Spanish National Research Council in Madrid, builds automated pipelines that apply consistent corrections to each dataset. This preserves comparability across time, but it does increase computing demand and processing delay. As datasets grow, pattern recognition becomes increasingly necessary. Biology is not identified by a single gas. It is identified by relationships between multiple variables that persist together. Humans simply cannot manually compare thousands of spectra across time and conditions. Machine learning systems combine similar spectra into groups. They then flag unusual combinations that differ from expected physical patterns. These systems rely on training data generated from physical models. If those models are incomplete, the resulting classifications inherit that bias, reducing reliability. Artificial intelligence plays an increasingly important role in this process. It does not simply decide whether life exists. Instead, it evaluates whether observations follow known physical rules. Sequence models predict how atmospheres change under radiation and chemistry when no biological processes are present. When real measurements match those predictions, non-biological explanations remain sufficient. When they consistently diverge, alternative explanations are required. These systems function as filters that remove physically inconsistent scenarios, rather than as sources of conclusions. Chemical disequilibrium introduces another boundary. There are some combinations of gases which react quite quickly and shouldn't coexist for long under stable conditions. When we do find them together, it implies there's some ongoing replacement by a particular process, possibly biological. Detecting this isn't simple. It means measuring several gases at the same time, and only when there is high confidence. But instrument drift can create false correlations by shifting measurements unevenly. That's why cross-checking independent measurements becomes absolutely essential before we can treat disequilibrium as meaningful evidence of potential life. Direct imaging changes how we observe planets by altering the geometry. Instead of relying on transits, telescopes actually block starlight and isolate planetary light directly. But this method introduces some alignment and contrast challenges, since starlight is much brighter than planetary light. Even small errors can allow starlight to completely overwhelm the planet's signal. There's a national observatory, run by the Commonwealth Scientific and Industrial Research Organisation in Canberra, that develops scattering models to separate surface reflection from clouds. Direct imaging gives us global atmospheric averages, rather than just edge-based views. At this stage of the analysis, spatial variation becomes important. Non-living processes usually smooth out atmospheric composition over time, thanks to mixing. But localized sources create gradients that resist this smoothing. Detecting these gradients requires enough spatial resolution and repeated views as the planet rotates. If the resolution is too low, those gradients will disappear into averages. Low resolution can remove an important way to distinguish uniform chemistry from localized activity. Survey strategy introduces unavoidable trade-offs. telescope time is limited and must be allocated carefully. Deep observation improves confidence for a few planets, but leaves most unexplored. Broad surveys find many candidates, but with less certainty for each one. Engineers must choose how to allocate time, because both approaches cannot be maximized at once. This choice shapes how biological inference develops. Comparative planetology depends on consistency across environments. Lifeless planets, for instance, help define the ranges of stable atmospheric behavior under known physics. Planets that fall outside these ranges definitely demand explanation. When similar deviations show up in unrelated systems, rare non-biological explanations start to lose plausibility. So then patterns across environments often matter more than the strength of any single signal. System integration limits progress just as much as hardware does. Better optics, for example, generate more data, and more data increases the processing demand. Processing limits, though, can slow interpretation when systems aren't matched properly. If sensing and computing advance at different rates, backlogs will grow. Therefore, effective progress requires matching collection capability with analysis capacity, making sure information can be interpreted as fast as it's gathered. Physical travel, at least for now, remains confined to nearby worlds. Direct sampling would, of course, provide certainty, but it just can't scale beyond the solar system. Remote sensing, therefore, acts as a filter to identify which planets deserve future attention. Errors at this stage waste limited resources and time, making accuracy an operational requirement. Over the next 10 years, improvements in optics, stabilization, computation, and artificial intelligence will very likely greatly expand what can be inferred from distant light. These advances don't remove physical limits, but they do allow observations to approach those limits more closely. By treating planets as dynamic systems governed by constraints, scientists move from simply asking where life could exist to actually identifying where inorganic explanations no longer suffice. Thank you very much for watching. Please like and subscribe.